This is a continuation of Chapter 3, and it involves a few problems, but that includes some drawings. In statistics, when they say that a distribution is normal, it means that it fits on a bell curve as you see in the diagram. Let's say that we measure the heights of many men, and we find that the mean is 176 centimeters, and the standard deviation is 7 centimeters. So in our curve then, right in the middle, we put that the mean is 176 centimeters. The empirical rule says that 68% of all men will be between plus or minus 1 standard deviation, and 95% will be between plus or minus 2 standard deviations, and finally, 99.7% of all men will be between plus or minus 3 standard deviations. If we then add and subtract the standard deviations to the mean and then plot on the graph, and then we can get a visual representation of the heights of men in our sample. Let's take a sample of 6 men of different heights, and then let's find the mean by taking the sum of all the elements and dividing it by n, which is in this case is 6. What we've done is we found the mean, which is 69.2 inches, but now we need to find the standard deviation using the formula we've done before. We make a table of x minus bar x squared. That is, we take each element and subtract the standard deviation and then square it. And then finally, we're going to sum all of these numbers together. Next, we take the standard deviation and divide by bar x and multiply times 100%. The idea is we have calculated with the coefficient of variations how far is the standard deviation from bar x. Here is an interesting example involving President William McKinley. He was 67 inches tall, or 5 foot 7 inches. The past presidents had a mean height of 71.5 inches and a standard deviation of 2.1 inch. The difference between McKinley and past presidents then is 71.5 minus 67 inches, which is 4.5 inches. Then the next question is, how many standard deviations is this? Well, it's 4.5 divided by 2.1, which equals 2.14. 2.14 standard deviations. Next, we identify a new quantity called the z-score, which is x minus bar x divided by s. In other words, 67 inches minus 71.5 divided by 2.1 inches, which gives us a negative number, negative 2.14. The z-score expresses different measurements in terms of standard deviation and also makes it easier to apply the empirical rule. If we say that a z-score between negative 2z and positive 2z is usual, then William McKinley at negative 2.14z is unusually shorter than past presidents. By the way, McKinley has seen a great deal of combat in the Civil War when he was only a private first class and very young. And later on, he worked his way up, became president, and was considered a very good president until he was assassinated in 1901. Here is an example involving regular corn seeds, and the measurements are given in pounds per acre. The data is arranged in ascending order, which allows us to see that there are 11 elements, that the minimum is 1316 and the maximum is 2496, and the median is the number right in the middle, which in this case is 1910. We use a formula from page 115 in the textbooks, which relates quartiles to percentile. That is, the first quartile is 25%, the second quartile is 50%, and the third quartile is 75%. The second quartile is easy to understand since it's the 50th percentile. That is, it must be the median, which is 1910. To calculate the first quartile, we use that special formula shown. And what that formula is giving us, it's saying that the first quartile is approximately equal to the third value of our data set. Likewise, the third quartile is approximately equal to the ninth value of our data set. Once we have calculated our values, we can create a box plot where we start with the extremes, the minimum and the maximum, and then we plot the quartiles in the box. And if you notice, you have the first quartile and the second and third quartile. The scale at the bottom is for reference purposes, and the idea is we can compare several box plot to see which one is has more variation, which one is wider, which has different extremes.